Where? No, the fluid that is displacing the weight of the helium, which is the balloon, right? So the buoyancy force, which is the weight of the air displaced, is greater than the balloon.
I was asking if there's also buoyancy force in the air. Is it only in fluid?
No. It's in liquid and air. That's the reason that you have it. Otherwise, we cannot go to planes. All this, if there is no buoyancy force, we won't see helicopter or planes or whatever, you know. So, because it's fluid, when I said fluid, I said liquid or gas. So, in this case, here, in this example, why this is the condition for floating, that the buoyancy force have to be greater or equal than mg. If mg is greater than this, what will happen? It will sink. And then I cannot apply the Newton's first law, what is thinking, unless that is moving at constant velocity. What Newton law I have to apply? When it's sinking. The second law. So when that cruise, that the guy, the captain left the cruise in Italy, you remember? When that happens, so I mean we laugh now, but it's very sad story. What happened at that time? The guy left, okay, it was sinking, it was not at constant velocity, probably was accelerating, right? So we have to use here mg minus buoyancy force equal to ma, because it was accelerating probably, right? So this is the, you know, the way that the same thing that we applied before, we apply now. Now, when we talk about buoyancy, yes, it's in equilibrium along y, okay, for the most part. Good. Why the object float? In addition to that, so we can say, and this is an example, let's say that this is an object that is 1/3 of the volume, 1/3 of the volume of the object is submerged. 1/3 of the volume of the object is submerged. So, applying the condition for floating, I can say that the buoyancy force on that object will be equal to mg of the object. If 1/3 of the volume is inside water, what will be the buoyancy force? According to the definition, Archimedes' principle will be the density of the fluid, let's say that is water, right? The density of fluid. Time, what? The volume of the fluid displaced. In this case, equal to mg. What is m in terms of the density of the object? Rho of the object times what? Volume of the object times gravity. What happened to the gravity? Cancels out. So why the object is floating? Because the density of the, now if this, how much is this? How much is displaced? In this case, how much is displaced? So will be displaced if inside here, let's say that is 2/3. Inside. Right? If it's 2/3 inside, so we replace, how much will be displaced? 2/3. So I replace this by 2/3 of volume of the object equal density of the object times volume of the object. This cancels out, and we get that the density of the object is 2/3 the density of the fluid. In other words, the density of the object is less dense than the density of the fluid. And this is the reason that the object floats. And this is due to the buoyancy force. Can you see that? So, why then the cruise normally doesn't think? What is higher? The water or the salt, the ocean water, or the density of the ship? What is higher? The water. And you will say, wow, why the water will be more dense than the ship? But remember that the ship, what has at the bottom? So it's like this. What you see is like this. This, and Carnival, and Royal Caribbean, or whatever. But here, what we have? like something like this, like a beer or like this, whatever, but you have air here. So when you add the density, the mass of the whole chip over the volume and the regular shape, it will give that this density is less than the density of the water. Got it? And this is the reason that the chip doesn't think. Any questions on that? Another typical example, and this is basically what you have to do when you have a partial volume. So you cannot say that the whole volume is the volume of the object because it's not completely submerged.